Welcome everyone. This is the last video on Euler-Lagrange and Lagrangian mechanics, which will deal with illustrating how to do a very hard problem. And this problem deals with a very simple dynamical system, let us say mechanical system. It consists of some hinge, let us say some kind of rigid support like this. And there's a hinge, you can suspend a rod. This is some rod. Basically, it's like a compound pendulum. This rod can oscillate in this plane of the board, and I have taken my z-axis, the z-axis, as this one. This is the direction of z-axis coming out of the plane of page. And by right hand thumb rule, you can figure out, obviously, the y-axis, the Cartesian axis y, must be this one. Let us make it name, okay, let it be y-axis or y1 for that instance, it helps. And so basically this rod has got a sleeve which can slide up and down along the length of the rod. It has got a sleeve, and that hinge point and the sleeve are connected together by means of a spring. There's a spring. So what does that mean of spring constant K? This sleeve can oscillate like this to and fro, up and down along the length of the rod, and this rod can oscillate like this. So it makes it a complicated resolution, like a kind of composition of two different motions. One along this one, like this, angular motion, rotation in this plane. This is the y-axis, and I will tell what my x-axis is. This is the z-axis coming out of the plane. This point is termed as A. Now I describe the rod as having mass m1. It has got some length L1. Let us denote the center of mass. This is the center of mass of rod. It is G1, and the moment of inertia of the rod along the ZZ1 axis about this point A, the moment of inertia given in the problem is this. And now I will describe the sleeve. This is the sleeve which has got this as the center of mass. So the sleeve is described as having some mass m2. It can slide freely along the length of the rod, having some length L2. Its center of mass denoted as G2. Its moment of inertia about G2, the center of mass. Moment of inertia of sleeve about center of mass is G2 I ZZ1. Okay, ZZ2. This is given in the problem. And what do we need to find? The equation of motion of this system. Give it a think. What can be the coordinates and how will they be generalized in the process of choosing them? Well, y is a Cartesian coordinate. So I choose my x1 as this one. This is my x1. This is the x-axis. Let me say this is the x-axis. And this is the y-axis. Like this. Making some sense, right? And this is my z-axis coming out. So basically now let me say that this motion of this rod has got 6 degrees of freedom. And the motion of the sleeve has got 6 degrees of freedom until and unless we specify some conditions. Like the rod can rotate in many directions, and there are 6 possible such directions, choosing x and y as Cartesian plane and z as another one. So we are working in the Cartesian coordinate space. So basically they turn out to be generalized in this case. I'm going to show how that is, but first let me tell you that there are only 2 rigid bodies in this whole system. Mass of the sleeve, this is one rigid body, and the rod itself is a rigid body. Rod will oscillate, mass will go up and down and oscillate along with the rod in process of doing so. And to set this system in motion, I will apply some external periodic force in this direction, which will always be horizontal like this. That's F of t, which is again some periodic force F0 cos omega t. Okay, this is how I've described F of t. So there are 2 rigid bodies. How many degrees of freedom does each rigid body have? Can you tell me? Well, there are. each rigid body without any restriction can have 6 degrees of freedom. That makes the system having 12 degrees of freedom total. But I am confining the motion of this system in this plane of the board, and it can rotate about this z-axis. It can rotate like this, right? It is rotating along the z-axis, rotating like this, and it can move in this xy plane. So basically each rigid body, the rod and the sleeve, will have only 3 degrees of freedom. Like we have restricted rotation along the xy axis and translation or some deflection along the z-axis, that is restricted. So that makes each rigid body have 3 degrees of freedom. That makes for this problem, this system has got 6 degrees of freedom. Now give it a think, give the video a pause and think, how many coordinates do we need and how many degrees of freedom does this actually have for the purpose of solving. Give it a think and let me proceed with my part. I'm also giving that L0 is the unstretched natural length of the spring. Unstretched natural length of the spring. Right? This is the spring, which is only till this much. And then the sleeve starts. And the spring is attached to this point. And the rod can oscillate. So think, how many coordinates will you choose? What are the coordinates apart from x1, y1 and z, and how are they independent, complete, and making the system holonomic? So I hope you have got some inference from this that this is a possible coordinate, theta, right? We can choose theta as an angular coordinate along this normal. This will be the natural position of the system, this vertical line. And so theta is a coordinate, possible coordinate. And so we have 3 coordinates to describe 3 degrees of freedom. And that makes the system holonomic, no problem. Independent, yes, if you freeze theta, the block can still oscillate. If you fix y1, the thing can still move. And if you fix x1, the thing can still move. There will still be some motion. So that makes it independent as well. So our coordinates along x1 and theta are generalized coordinates. Let me tell, I mentioned something wrong before, that we here have only 2 coordinates and thereby 2 degrees of freedom. As I said, give it a pause to the video and think. I meant to say that this rod can rotate in this direction. That is 1 degree of freedom, and block can oscillate up and down along length of rod. That is 1 degree of freedom. So that makes total 2 degrees of freedom, and we have 2 coordinates, x1 and theta. That y1 is just given for reference to find some other variables and stuff, but the main 2 coordinates which are generalized are x1 and theta. So, and we have 2 degrees of freedom, and in that sense it is holonomic. And we begin solving the problem. Look at the figure carefully, because now I'm going to rub it and write the expression of potential energy. Now what is the potential energy of this system? Well, the spring will do some kind of energy storing, and that makes the spring have some potential energy. So let me write this V as potential energy equal to half K. Now what do I write here? We generally write x1, but will x1 be the amount by which the spring will stretch? No, x1 minus, I've mentioned L0 was the natural length, so this is one amount by which the spring will stretch, and minus L2 by 2 whole squared. This total quantity gives the amount by which the spring will actually stretch, because if you remember the diagram, from the diagram, this rod was hinged at this point, there was a mass point, the spring was from here to here, so you have to subtract this much length. This small length is L2 by 2. L2 is the length of the sleeve, so L2 by 2 needs to be subtracted from this whole x1, and then we have the unstretched length L0 and the vertical position, that also needs to be subtracted. So with the net expression for the potential energy due to spring is this, okay, plus, now what will we add? The gravitational potential energy of the rod. How much is it? It's very easy, m1 g L1 by 2 1 minus cos theta. This is the gravitational potential energy of our rod. Basically this is the amount del H, the change in height underwent by that center of mass of the rod when it oscillates. This is the equilibrium position. So this is the change in height. I'm talking about this as del H. And this quantity turns out to be L1 by 2 into 1 minus cos theta, because the length of the rod is L1. So this term is L1 by 2, and I took this as theta. So subsequently you get this expression as the expression for your potential energy due to mass of rod. Now what are we left with? Potential energy of the sleeve. Yes, what is that? Now for the sleeve it's a bit complicated, a big expression. It is plus m2 g. I will first write the initial positions configurational potential energy, that is L0 plus L2 by 2. I'll explain why. This is the initial potential energy. As you see, the spring, the sleeve was like at this point, this length at the equilibrium position, this length at the equilibrium position will be L0, the unstretched length of spring, and the length of the sleeve is L2, so L2 by 2. The center of mass is what we are concerned about to find potential energy. The center of mass is at a height of L0 plus L2 by 2 from the point of suspension, and basically this is the initial height at which our sleeve is. This is the initial height at which our sleeve is when it oscillates. Now when it oscillates, you cannot do something like some length minus this one. No, that when it will oscillate, that x1 length, which x1 is varying, our coordinate x1 is varying, and if it is varying, then we have to consider x1 as the final configuration times the cos theta in the direction of this initial configuration, by which I mean this energy, this one, needs to be subtracted like this. We need to subtract this variational height from this initial absolute configuration to get the net potential energy of her sleeve, and this is the total expression of potential energy of the whole system. Okay, give it a look, write it down somewhere, because now I'm going to rub it off. I hope you have noted down. So I think I have to plug in the charger. Yeah, there's a way out. So by the meantime, you just simply write this down and think about why I wrote the expression of the sleeve the way I have. So it's basically this expression you are getting. And let us fix the camera. Yeah, it's visible, I guess. Yeah, it's visible. Now I will rub this off, and now basically we are going to think about the kinetic energy of our system. Now what is the kinetic energy of our system? Remember, for kinetic energy we have two types of terms: rotation and translation. Rod will translate, rod will rotate, oscillate. Rod will oscillate like this about the hinged point, right? So that is rotation. That will contribute some rotational kinetic energy to the rod and to the sleeve, and sleeve will go up and down. That will contribute to some translational kinetic energy to the sleeve, and the rod is also having some translational motion along this type of an oscillatory motion. So we can have two terms of translational kinetic energy, two terms of rotational kinetic energy, and for translational motion we have to define the velocities we are considering. The velocities will be of the velocities of the center of masses. So what are we getting as an expression of kinetic energy rotational? It is basically half AIZZ1 plus half G2 I ZZ1. This is 1 G1 I ZZ1, and so now we are having, okay, so sorry, this is 2, this is also 2, So if you remember, this is the moment of inertia of, this term is the moment of inertia of the sleeve about its center of mass. This is the moment of inertia of the rod about point A, and basically this thing is multiplied with theta dot squared. Theta dot is omega, the angular speed, and that's squared. So if you remember from your rotational mechanics, that the kinetic energy due to rotational motion is half I omega square, and I have summed the rotational kinetic energies of each rigid body and added it up. And now time for our translational motion. So that is half m2 some v0 g2 dotted with v0 g2. Basically it's v0 g2 whole squared. Now this simple term means the net velocity of the center of mass of the sleeve in the inertial frame. So how do we define this v0 z2? The net velocity of center of mass of sleeve, well, it is x dot I cap plus theta dot x1 j cap. Now what is x dot I cap? The velocity of the sleeve along x direction, some translational motion. It was going like this, the sleeve, and this is basically, this expression is the linear speed due to the rotation. If the rod is moving like this in this plane, some theta through some theta, then that theta dot is omega, and omega times that moment term x1 gives you omega r, that is the linear speed due to rotation, and this is the linear speed due to translational motion, and this is the net, this is the total velocity of this center of mass of sleeve. So this is the expression which we are going to substitute here and self dot product itself, self dot it, we will get the kinetic energy, and we will also have two coordinates in this problem. One is x and the other is theta. So we have to go through Lagrange's approach twice. One for the x equation, the force equation. Let us see if it turns out to be the force equation for x or not. I can foresee that. And one for the theta, which might turn out to be the torque equation. It must be, right? From intuition we can say. We will get two equations to completely describe the system. Now in this case, yeah, so we are done this much. So how do we proceed? Now if you remember, we will do that 1, 2, 3 LHS and 4 RHS that way. So what is our first term of the Euler-Lagrange? We have our T and V with us. So what is our first term of Euler-Lagrange? It is applying Lagrange for this x1 direction, variation of x1. What is our first term? I don't want to confuse you people. So basically the first term is first order derivative of this, right? And what is that? With respect to x1 dot, if you do the partial derivative, you're going to get m2 x1 dot, and dy dt gives it another dot. This is simplified, the first term. What is the second term? It is basically partial minus partial t partial x. What is that? Minus m2 x1 theta dot squared. You can do this partial with respect to x1, and x dot will be 0 for that case. And now you observe something very important. Was it not much intuitive, and was it not logical that since our system is rotating, there must be some centripetal term, some centripetal expression in this? Yeah, so as you can see, isn't this expression a centripetal term as we had expected for such a system we had described? This is a centripetal term, and this indicates that, yeah, we are going in the right direction. Minus m2 x1 theta dot squared basically is m omega r square, m omega square r, the centripetal force expression. This is the centripetal force acting on our system, m omega r square. Now that turns out to be m2 x1 theta dot squared, but the meaning is that centripetal term. This is the centripetal force. And what is the third term? Okay, I'm not rubbing this. What is the third term? The third expression, is it visible? Yeah, I hope it's visible. And the third expression turns out to be partial, positive partial v with respect to partial x. And that is basically, oh, it gets tilted. Yeah, so that's k times x1 minus L0 minus L2 by 2 minus, it's visible, yeah, minus m2g cos theta. Yeah, it's visible, right? Yeah. So this is the third expression we are getting. And so what is our LHS? If we add them, we get our LHS, right? So I write the LHS for once, then I'll rub it off to get the RHS. So our LHS turns out to be, LHS is equal to m2 x1 double dot minus, oops, yeah, m2 x1 double dot minus m2 x1 theta dot squared plus this term minus m2g cosine of theta. Yeah, so this is basically our LHS. This full expression is our LHS, right? Remember this, note it down. I'm giving some time, and then we are beginning the computation of RHS. Yeah, I'm doing the RHS in red because this is more important at this point of time. This is a very important idea. So now we need to find the generalized force in the x direction. X is the coordinate for which we are doing the Lagrange the first time. So if you remember the diagram, this was the point A, a rod was like this, and this was some normal, this was our sleeve, this was the spring, this was the mass m2, rod is of mass m1, all the lengths, moments of inertia, everything defined. This center of mass is g1, this one has got center of mass g2, and in this case, okay, let us make it a bit clearer because I'm going to denote the forces somewhere. So basically, this is the rod, this is the sleeve, and there's some spring that's immaterial, and now there is this angle defined as theta. I took this as the y direction. What does that mean? That means this is the y axis and the unit vector along y axis is j hat, right?